Hello and welcome to another edition of Maths at Derby tutorials. I'm Natalie as usual and I have with me today Jake.
Hello, how are you doing?
Yeah, good, thank you. Thank you for joining us. And we're both in the same maths class and I thought we'd go through a example today that we did in class. But before I do, I thought I'd just put you on the spot, Jake, and ask you, what's the sum of the first 10 numbers, 1 to 10?
That's 55.
That was quick. So how did you do it?
So we can make pairs of 11, and then there'll be 5 pairs of 11. So 10 and 1, 9 and 2, 8 and 3, 7 and 4, and then 5 and 6. That's your 5 pairs. And there's 5 lots of those pairs, so 5 times 5.5, which is...
And that's like a smart...
50, sorry, not 5 times 5.5, 10 times 5.5, which is 55.
And that's like the Gaussian formula.
Yeah, so back in the, I think it's the 17th century, Gauss was asked by his teacher, who was probably completely fed up of the class by that point, to sum the first 100 numbers. And the teacher obviously expected them to sit and go 1 plus 2 is 3, plus 3 is 6, plus 4 is 10, and so on and so on and so on.
But he turned around
But he
and
just
said,
went, done. And obviously the teacher was in complete amazement, did not expect the response to be so quick. And it turns out that Gauss noticed that he could pair the numbers from 1 to 100 in pairs of 101. So like we did there with the pairs of 11, he did pairs of
so in that sense,
101. So he did 50 pairs of 101, so it's 5,050.
you're a bit like Gauss, really.
No. I mean, as much as I'd like to be,
no, you
but
are
like...
smart, Jake, to be fair. Yeah, well, should we have a go at proving it, that that's actually true?
So should we have a look at what I prepared earlier?
Take it away.
Okay, so this is the
Cool.
Gaussian formula using the sigma notation that we will have come across in class. So it's saying that the sum from the first n numbers is n divided by 2 times by n plus 1.
So that's the formula that, the sort of like magic trick that he came up with.
Yeah, and we can double check that it works for what we've just talked about. So let's put 10 in. So the sum of the first 10 numbers is 10 divided by 2, which is...
5, yeah, I can do that.
Times by 10 plus 1, well that's 11. 5 times 11 is 55.
55,
and that seems right to me. And fingers crossed it is right,
but
we can prove that.
But we're being rigorously told that that's not enough, is it? We have to rigorously prove it.
Rigorous proof is definitely needed, as we've been told many, many times. So let's have a little look at the proof. So we're going to use a proof by mathematical induction here. Okay. And what that's essentially saying is that we're going to try and prove it for some case k. So that could be after the 6th term, it could be after the, I don't know, 600th term if we're summing to 1,000, for example. And then from there, we are going to say if we can prove it for the next case on, then we can prove it for the case after that, the case after that, and so on. And therefore, we're just going to say it's proven.
So just a bit like dominoes?
Yeah, essentially a bit like dominoes. That's a really good idea.
Yeah. So what you're doing with this formula, though, you're just going to replace the n with k. So n is your kind of generic, and then you're just going to drop k in and say, well, what about k, which could be any number?
Yeah.
Okay.
So let's have a little look. So before we can even start, we need to do what's called a base case. And a base case is just checking that it works for the smallest number that we think we can put into it.
Or
so we're going to say
get away with.
Yeah, we can get away with. So we're going to say we're summing from 1 in all of these cases. So if we just check it, so the left-hand side of the formula was a sum from 1 to n, but in this case n is 1.
So and essentially what we're saying by that kind of fancy formula is that we're just saying, look, just count them manually on the left-hand side. You know, do it laboriously. 1, 2, 3, 4. Oh yeah, it works. But in this case, we're just doing it for the number 1. Yeah. So 1 all to 1 is 1. Yeah.
Simple. And then plugging it into the formula, half of 1 times 1, 1 plus 1 even is 1. So that's right. So the left-hand side is equal to the right-hand side, which means that the statement is true when n equals 1. And now we can assume, with the induction hypothesis, that it's true when n equals k. And we're saying that here k is an element of positive natural numbers. So that's any whole number from 1. So 1, 2, 3, 4, 5, etc.
I thought about this as well. I mean, could it have 0 in there as well? Because 0 doesn't make any difference, does it?
Yeah, it could have 0 in this case, because 0 divided by 2 is 0, and then the sum of 0 numbers
I just thought of that.
We just think we can start from 1, because why not? Because that's what Gauss did. Let's do what Gauss
let's
did.
do what Gauss did. And it seems obvious and sensible as well. Okay, cool.
So now that we've assumed that it's true when n equals k, we need to try and prove it for the next step on. So let's assume let's consider the case n equals k plus 1.
Okay.
And we can express that as a split of the sum. So we're summing from 1 to k plus 1, but we can write that as 1 to k plus the sum from k plus 1 to k plus 1.
That seems a bit fancy, that second one. So I know the first one, just, you know, say it was the 10 numbers, that's just manually, again, sort of 1 to 10. Yeah. But the other one is just k plus 1 to k plus 1. That's like the base case almost, isn't it?
Yeah, it's exactly that, pretty much. So it is just k plus 1. Yeah. So let's have a little look. So we've got k plus 1.
Yeah.
And then because we assumed that the kth case is true, we can replace this I equals 1 to k, the sum of the first k numbers, with the formula that we've assumed. So k over 2, lots of k plus 1. Then we're going to have the extra k plus 1 term at the end.
Yeah.
So from there, that we can get closer to the formulae that we want.
So essentially, I mean, you're just putting, you're going to be replacing all those with the k plus 1. So you're just like algebraically rearranging it and hoping that it looks like the original formula, but with k plus 1 in it instead of k instead.
Perfect, yeah. So we're going to factorise out. So we can factorise out a factor of k plus 1, and then that gives us k over 2 plus 1. Well, that looks slightly closer, but we're going to have to sort out this fraction, which we just don't like at the moment.
Yeah.
So using our rules way back to GCSE, we can sort this fraction out. So it should be k plus 2 over 2. And because it doesn't matter where the over 2 goes, because it's multiplication, we can move it across.
And that's looking a lot more like it as well. So you put the 2 on the other side, and then you've got this sort of k plus 1 plus 1. So you turn the k plus 2 into k plus 1 plus 1.
And that then is exactly the form that we had originally.
Oh, so you've proven it.
So that is it. That concludes the inductive step. So we can say, hence, proven by the principle of mathematical induction for its full name.
And you've drawn and then
we get to draw our favourite Helmholtz square to say that the proof is done.
It's done, yeah.
It's done.
It's done. We love that. We love that square. Well, that's okay. So we've proven it. That's brilliant. I think that's a job well done. And yeah, I think we're kind of off to calculus now.
Off to calculus, yep.
Yeah. And which starts at 5 o'clock because you're a student rep.
Yes,
well,
that's true, yeah.
And
so we managed to get it moved down to 5 o'clock, which is excellent.
Amazing. That's why I hang around with Jake, because he's got all this power. But anyway, thank you very much to from Maths at Derby. See you again soon.